Hello Monster Gardeners and welcome back to the Test Lab. My name's Dr. Watt and today we'll be continuing our journey down the LED rabbit hole after the last episode's revelation that LED grow lights can finally compete almost on level terms with gas discharge lighting. Next up in our quest for answers is the coincidentally named Next LED lighting company that viewers of What's in Store will already be familiar with, as Scott reviewed them a little while back. And a unit's even been happily growing peppers in our current culture system for the last few months. Now I've gotten hold of my own units to test them with the full backing of Next LED themselves. This means we can all look forward to our first look at a completely different design philosophy from that employed on the very impressive Spectrum Kings. Because whereas the Spectrum Kings had a small number of high brightness LED chips on a circuit board, these Next units use lower power LEDs but far more of them in a larger array. And yet the Next LED unit isn't really all that heavy, despite its size. In addition, the biggest Next unit, the Mega, draws similar power to the SK600. But why are they so different? In a word, packaging. In the microelectronics world, the word packaging doesn't refer to cardboard boxes or bags of foam peanuts. It instead refers to the materials and structures used to protect the component inside from the dirty, smelly, ugly real world that you and I live in. Electronic components are small, really small. Even 30 years ago, the circuits on some of these components were measured in terms of the width of a human hair, in microns. But today, many electronic devices have circuitry on the nanometer scale. That's just a step up from atoms. Now, on scales as small as these, everyday stuff like dust and electrostatic electricity become lethal to these tiny circuits. And so, we're forced to encapsulate or package these tiny devices to protect them from the elements. And the package itself often defines the characteristics and performance of the device it contains. For each device in existence, there are many different methods of packaging it for different applications and uses. And this is especially true for the light-emitting diode. So, in order to understand the benefits and limitations of different grow lights out there, it helps to at least understand the basic types of LED device and package that are being used. But, in keeping with the TESTLAB mantra, we're going to keep this simple. So we're not going to look at all LED package types, as that would take ages. Instead, we'll focus on those most used in horticultural grow lights. Also, because we're diving into some rather chewy physics here, we'll be skipping over a lot of the hard science and keeping this all conceptual. Okay, so to kick off, I'm going to assume that you've watched the Spectrum King test episode, and so you know at least what an LED is and its basic functionality. The next step is to understand the types of packaged LEDs and their various advantages and disadvantages. Unlike gas discharge technologies that require heat to function, heat is in fact the enemy of the LED, which is unfortunate because heat is also a byproduct of the same reaction that creates the light. So, more light equals more heat. For a very long time, this issue limited the usefulness of LEDs, But in the last 20 years, a technology and materials revolution across the entire microelectronics industry has changed things greatly, and packaging has played one of the biggest roles. The heat problem is a simple one to understand. As we add more power to the diode in order to get more light, more heat is also generated. But too much heat, and individual components like the solder that connects the wire to the chip will fail. So we either have to turn the power down and figure out how to get more light from the same source, which is essentially increasing its efficiency, or we can address the heat issue somehow by figuring out some way to evacuate the heat from the chip faster and more effectively, which in turn allows us to turn up the power and get more light that way. Or we can do a mixture of both. And it's this engineering compromise that's at the heart of all the complexity in the LED market. High power versus high efficiency. Modern LEDs can be broken down into three main categories. Miniaturized LEDs, which are probably the ones you're most familiar with. High power LEDs, which are not to be confused with high brightness LEDs. Yes, they are often the same thing, as more power should equal more brightness, but in the LED world it depends greatly on what the LED is being used for. High brightness refers to output, and that can also be achieved through having lots of low power devices in an array or a fewer number of higher power devices. So don't be fooled. High power refers to the juice going in and not what's coming out. The final general category of modern LEDs is called application-specific LEDs, which is a fancy way of saying LEDs built for a specific purpose or thing. It refers to things like alphanumeric displays or digital RGB chips for signs, or things like filaments for old-style light bulbs. Even some grow lights use these type of application-specific LEDs, most obviously bi- and tri-coloured LEDs. But as the Spectrum King and Next are both sunlight mimicking units, we'll save the application-specific devices for when we test an adjustable spectrum grow light, because the whole spectrum issue is a can of worms that will take up too much time to address here. So today we'll focus on sunlight or white LEDs, which in itself is an oxymoron. You see, actually there's no such thing as a white LED. All white LEDs are either blue or red LEDs with a phosphor coating, which is what dictates the final spectral output. This is the reason that many white LEDs have such poor orange to red spectral ranges. It's because it's converted blue light. However, there is a new generation of devices just on the horizon that use purple LEDs, and combined with new color correction materials, they could be the most sun-like spectrum of all. Phosphor is such an important part of white LEDs that most phosphor recipes remain some of the most jealously guarded secrets among the LED manufacturers. Now, we can't move on with the discussion until we mention the final part of the LED knowledge jigsaw, and that is LED arrays. You see, the LED itself is just a component. It's got to be mounted on something to supply it with power, and if necessary to dissipate its heat. But the array greatly depends on the package chip itself. So let's concentrate on the three main types that are used in the vast majority of white spectrum LED grow lights. First up is the surface mount device, or SMD, which comes in all shapes and sizes. Most SMDs are usually low to mid power and can be mounted to almost anything without worrying too much about heat buildup. The higher the power of the surface mount device, the more heat it produces. This means mounting it to a ceramic or metallic circuit board in order to act as a heat sink. But the heat transfer between the package and the board isn't as efficient as mounting the bare chip directly onto the board or heatsink itself. And that's the main advantage of the second LED type. The COB, or chip on board, is an LED device directly mounted to the heatsink or circuit board, which aids greatly in heat transfer. But hey, why stop at one? That's what MCOBs, or multi-chip on board arrays, are all about. They sometimes look like just one chip, but in fact they house many diodes. But more diodes means more heat, which means a bigger heat sink. Heat also kills the bonding wires, and one way to address that is to remove them and flip the chip over, directly connecting the anode and cathode to the circuit board via a bonding pad. This allows us to make the chip much more resistant to heat, while also removing shadows caused by the bonding wires themselves. So, some COBs are also flip chip devices, and MCOBs are also flip chip arrays, but it's hard to tell underneath the phosphor cap. But either regular or flip chip types of COB and MCOB have to be mounted directly to a very serious heatsink in order to address the sheer amount of heat they generate. Because that's the trade-off. More power equals more heat. Flip chip itself is a packaging technique that was borrowed from the computer chip industry. And another technology is also making the migration. The chip scale package, or CSP. This is the newest of the packaging technologies. The phosphor cap now forms part of the package itself, which allows more visible light to escape the package, while at the same time allowing the package architecture to be more simplified. This means that they're both more robust and efficient. With LED grow lights being so specialised, don't be surprised to see a variety of these different package technologies used in tandem. However, that's just the package devices themselves. They still need to be mounted to a means of power supply and, where necessary, to a type of heatsink, like a ceramic circuit board. And now you have an LED array. The layout and design of the array is dictated by the properties of the device that's used. More light generally means more heat, and so a large heatsink or circuit board clearly denotes powerful LEDs. So what does this all mean? Well, if the fixture in question has a large number of individually packaged LEDs that are mounted without any need for heat dissipation trickery, then they're probably low to mid power surface mount devices that generally run pretty cool. On the other hand, if you see an array of devices with lenses of some kind mounted to a serious looking ceramic circuit board, then you're most likely dealing with high power LEDs. And if you look closely at the devices themselves, you can even take a guess at what type of LED components are being used. The lower power surface mount devices are prevalent in more close proximity fixtures, as they won't burn your plants with either too much light or heat. This means less light is used, and therefore it's a more efficient approach, meaning the production garden is more efficient, or so the argument goes. The higher power chip on board, multi-chip on board and chip scale packaging devices that are arranged in an array are designed for a more traditional fixture, using heights of 30 or more inches. This makes them more familiar to the typical gardener. Which is the better approach? Well, that's a question that entirely depends on your localized conditions. But as per usual here at the TESTLAB, we're just here to present you the data and base our own conclusions on that. So, as with last episode's Spectrum King test, we'll be using one of our two specialised LED tests to gather samples from the next fixtures. The lower intensity fixtures, that's the 160 watt Mini and the 190 watt Veg 8, will be tested on our 4x4 overlay grid in the 10x5 tent, where we'll be gathering the usual conditions data and 16 ppfd samples per layer at each of 4 heights, 12, 18, 24 and 30 inches. The higher intensity fixture, the Mega, will be tested on the 5x5 grid at heights of 24, 30, 36, 42 and 48 inches for a total of 125 samples. And that takes some time, so let's get cracking. This second batch of LED fixtures highlights the issues that surround the whole LED phenomenon, and that is choosing the right lights for the right scenarios. The next approach to luminar design is almost the exact opposite to that of Spectrum King, and the results on the Mega just have me asking more questions. But before we get to those, let's take a look at the lower intensity offerings, which to the naked eye look like scaled back modular versions of their big brother. We don't really have anything to compare them to at present, as although the Spectrum King closet case is close to the 160 watt Mini in footprint, we only tested the 100 watt version, which is nowhere near a fair comparison. So these numbers for the 160 watt Mini and the 190 watt Veg 8 stand as benchmarks. Both the Mini and Veg 8 share the same design philosophy as their more powerful sibling, but due to the lower power rating, they're obviously aimed at more low intensity scenarios, with the Veg 8 being named for its purpose as a T5 replacement. The hood design acts as a perfect heatsink to all of the next fixtures, and it's hard to believe that this is by mistake. The Mini's main difference to the larger footprint Veg 8 is the addition of a polymer screen of some kind, which we guess is for further light dispersal and in order to ensure that no hotspots occur as plants grow up into the canopy. Again, good design for the purpose. The 4x4x4 test actually feels a little unfair to the Veg 8, as it's obviously aimed at the fluorescent tube market, so a slightly lower and narrower test would be much more in line with its design philosophy. Now it's time for the Mega. The already deep impact caused by the SK600's numbers being as close as spit to a DE-HPS greenhouse fixture turned into a real coffee spitting moment when we looked at the Mega's numbers. They comfortably beat the old SK600's numbers and make a DE-HPS look as old and thirsty as a Detroit V8. But before we get ahead of ourselves, I should note that the SK600 was already an old fixture when I tested it, due to all of the fun issues that constituted the first few episodes of Season 2. It's already been replaced by the SK602. And we didn't test the SK600 with the recommended reflector for the 5x5 area. So for this reason, I'm going to try and get hold of one to see how these two polar opposite design philosophies stack up. But for now, the next Mega takes the LED power crown, and nearly the ultimate power crown. That is the most powerful thing we've tested so far. Currently, that's the DE-HPS Genesis with the Radiant DE hood. It's the most intense reading we've ever taken in a full 5x5 test, and that was at a height of 48 inches. But this brings me to the trump card of the next: heat, or lack of it. The combination of Powerbox ballast, Radiant DE hood, and Genesis DE-HPS bulb came to be known as the death ray configuration in the TESTLAB, because it was so much brighter than any other lighting configuration we'd tested. But if we're honest, an LED's appeal is not just down to ultimate power. Really, it's about efficiency. How much light do you get for your money? And that's a harder question to answer because of the cost imparity between traditional HID and LED. Traditional HID technology is generally cheaper to buy, better known with decades of understanding and development behind it, but costs more to run. LED is the new kid on the block that's waving its tech at growers with promises of improved spectra, lower running costs, and longer life with hassle-free maintenance. But at a punch-you-in-the-wallet startup cost. So the big question is, which is better? In order to answer this question, we had to come up with a new way of looking at it. So we designed a new metric, which we call TEAC, or 3-year all-in cost. This new metric is actually pretty easy to work out and comes in 3 steps. Step 1 is to take the upfront cost of the fixture. Then step 2 is to work out any maintenance costs over the period of 3 years. The third step covers working out the electrical cost for 3 years, which we'll do using a standardized model of one fixture running for 12 hours per day for 3 years. And the light period total comes to 13,140 hours. To work out the economics, we use a rate of 17 cents per kilowatt hour, That's actually rounded down for the 17.6 cents per kilowatt hour we pay here in most of California. However, there is a caveat. We're using our own test numbers for these calculations, but it is obvious that bulbs and even LEDs degrade over time, and so the power draw will change. Seeing as that adds a level of complexity, we're just going to go ahead and ignore it, meaning that our TEAC calculations are all best case scenarios. So take this all with a pinch of salt. Now, in order not to drown you all in numbers, we've knocked together this handy chart to plot all the numbers on. The y-axis here represents the average output, and on the x-axis we'll be plotting the TEAC metric. As we've never looked at anything like TEAC before, it helps us to have a benchmark. That is, something we do understand to use as a point of reference. And what better to use than the Gavita Pro, probably the single most recognisable fixture design in all of horticulture. All our DE-HPS tests were conducted at 36 inches, which was due to our non-compounding tent, as with all our readings. Reflective surfaces, like reflective tents or reflective paint, will greatly increase readings, as will hanging more than one of these fixtures together due to the light compounding effect. But we only measure our test area and nothing else, so as you can see, the benchmark is still pretty high. The Gavita isn't the most powerful greenhouse fixture we've tested, but it makes up for that with its super low uniformity ratio at 2.1. This means that its most intense reading is only 2.1 times higher than its least intense spot. In other words, it has great uniformity. The major flaw, of course, with DE-HPS is the spectrum, which is why growers have gone searching for alternatives in the first place. But what is the cost? Well, the TEAC comes in at $3,253.76. So how does the SK600 stack up? Well, we took our reading from 30 inches for this matchup as uniformity skyrocketed to 10.2 at 24 inches and was still fairly high at 5.7 at 30. However, it's our guess that the 90-degree reflector will solve a lot of that based on the results from the SK400 versus the SK400 Plus. The spectrum is greatly improved over the DE-HPS, which is the obvious appeal of LED. But what keeps people away from LED is the upfront cost. So what does that look like after 3 years? The answer is $3,036.25, all in. That's over $200 cheaper over 3 years, despite that upfront cost. And it's just getting better from there. Spectrum King claimed 90% brightness after 3 years. So the longer you keep the fixture, the cheaper it becomes overall. So how does the Mega stack up to this? Well, its spectrum is similarly awesome to the Spectrum King, and we already know about its outputs, so what about the cost? That comes in at $3,126.87. Not quite as cheap as the SK600 due to the extra upfront cost, but over $100 cheaper than the Gavita, all for an average of 381.5 micromoles of ppfd and a uniformity ratio just over 3. But if it hopes to challenge the all-powerful death ray, we'll need to use the test numbers from 24 inches, where the TEAC stays the same, but the test numbers jump up to an average 447.98 micromoles of ppfd, and a uniformity still relatively low at 3.96. It shows how far LED has come. The Mega from Next and the SK600 or 602 from Spectrum King are like chalk and cheese in the market, being designed for completely different industrial garden situations. But they both show just why LED is so exciting. But wait, what about the death ray? Well, that's where it all falls apart a little bit. For a start, at 538.83 average micromoles of ppfd and a uniformity ratio of just 2.4, with this data taken at a height of 48 inches, you can see that in total power LED still has some catching up to do. But that's not the point. You could make a 1000 watt LED quite simply and blow the DE-HPS to dust. And that's an approach some companies are taking. But cost really is the driving force here. The reason to get excited over LED is the $100 to $200 saving per fixture over 3 years, matched to a better spectrum. If you multiply that by 20, or 200 or 1000, you begin to understand why commercial growers are just so wound up by LED. But what of the death rate? Surprisingly, its TAC is $3,103.21. And this is the conundrum that you have to face as a grower. The total cost for LED versus DE-HPS is now at parity over 3 years and improves in favour of LED over time. In fact, the next is rated at 100,000 hours, and if that's true, well, the game's certainly moved on. But LED doesn't have 30 years of understanding behind it, and every harvest is therefore a learning experience, for good or bad. So really it's down to circumstances. What does your garden look like? How big is it? What sort of growing environment do you use? Because now you have more choices than ever before, and it's just going to get better as LED develops. So that about wraps up this episode. Congrats to Next for the power crown and an excellent range of commercial fixtures. We're hoping that we can get hold of an SK602 to do our first completely pointless comparison, because these two fixtures are not really competitors. But before you go, make sure you subscribe to our YouTube channel, as you really don't want to miss what's coming up. And also follow us on Instagram or Facebook so that you're up to speed with all of our activities at Monster Gardens. Just one final word. I'll leave you with the knowledge that there are 5 Black Dog LEDs currently being tested in the TESTLAB. That's as well as a ton of other developments, so make sure to stay tuned. However, for now, my name's Dr. Watt, and thanks for watching the TESTLAB.